All right, so welcome and thanks for coming to this talk today. As she mentioned, I'm a software engineer at Braintree Payments. We're a subsidiary of PayPal, and we process credit card payment transactions for companies like Uber and Airbnb. Maybe you've heard of them. Maybe you used them yesterday to get to the hotel. Here's my Twitter handle. Not a lot of activity there, but more importantly, I think the GitHub link. At the end of this talk, there'll actually be a link to a repo on GitHub with all the information from this talk, as well as the slides and everything else. So, background. What inspired me to do this talk? A while back, I had an interview programming challenge posed to me that suggested that I implement a simulation of the game of war in a language of my choice, and the implication, of course, was that it be a procedural language. So I did that, and no, this wasn't at Braintree. You won't get this challenge if you submit a resume. But my thought afterwards was, what if I could do this in SQL? Why would you want to attend this talk? CTEs, or common table expressions, are a powerful tool, but the recursive keyword adds even more capability, but it's often very confusing, at least I think so. Hopefully this will be a fun way for you to learn the power of CTEs, but more importantly, recursive. Oops. All right, oh, there we go. So a roadmap, how are we going to accomplish that? First, we're going to describe the problem space using sets. Then we're going to examine two false starts that I made and discover some of the limitations of recursive common table expressions. We'll walk through and hopefully understand the working solution, and then I'll leave some time at the end for a Q&A. Fair warning, though, this is a code-heavy talk. I have tried to make sure that the size of the font on screen is large enough that you can read it, and I'll try to make enough time that you can see what's going on as I walk through it. But feel free to stop me if you want to look at that code again. So by way of review, what are recursive common table expressions? Well, let's start by looking at the docs for the definition of common table expressions themselves. They say this: the keyword with provides a way to write auxiliary statements for use in a larger query. These statements, which are often referred to as common table expressions, or CTEs, can be thought of as defining temporary tables that exist just for one query. Each auxiliary statement in a with clause can be a select, insert, update, or delete, and the with clause itself is attached to a primary statement that can also be a select, insert, update, or delete. Essentially, we can abstract portions of our query out into standalone queries for readability, reuse, and performance. As a side note, CTEs in Postgres currently are an optimization fence. The CTE will not be merged into the main query for purposes of the planner. This is both a blessing and a curse, but not really relevant to our talk today. So what about recursive? The docs say this: the optional keyword recursive modifier changes the keyword with from a mere syntactic convenience into a feature that accomplishes things not otherwise possible in standard SQL. Using the keyword recursive, a with query can refer to its own output. Now, if you're like me, you read this sentence or paragraph in the documentation and your first thought is, what? This blurb is not overwhelmingly helpful. It's technically accurate, but it doesn't really tell me why I would use this or how to use it. Basically, we can execute one query and then use the results of that query to query again for additional rows, and keep continuing to do that to build up our results set with this query and append cycle until we don't have any more additional results to add to our return set. Typically, people use the example of having, say, a table of employees. Each employee has a manager. It's self-referencing to that own table. And you're going to walk up the tree to find the whole, like someone's ultimate manager, for example. And you can't otherwise do this in SQL. You would end up doing multiple round trips to the database, which is obviously not ideal. Note, recursive common table expressions are actually implemented using iteration, not recursion. We can think of this as recursive function calls that have tail recursion optimization. And this is important because we don't want to blow up the stack based on how many times we quote unquote recurse. The docs actually call this out almost as if the feature shouldn't be called recursive, but I disagree. The mental model of the querying is most definitely recursive. So the word choice here is correct, but you don't have to worry about the implementation details. So the problem space for today's talk. How many of you are familiar with the card game War that maybe you've played as a kid? So some, but not all. We're going to start out with a standard deck of 53 cards, and Wikipedia has this to say. I guess 52 cards. Wikipedia has this to say. The deck is divided evenly among the players, giving each a down stack. In unison, each player reveals the top card of their deck. This is a battle, and the player with the higher card takes both of the cards played and moves them to their stack. If the two cards played are of equal value, then there is a war. Both players place the next card of their pile face down, depending on the variant, and then another card face up. The owner of the higher face-up card wins the war and adds all 6 or 10 cards on the table to the bottom of their deck. If the face-up cards are again equal, then the battle repeats with another set of face-up down cards. This repeats until one player's face-up card is higher than their opponent's. Now, for those of you who aren't familiar with the game, thinking through this scenario, you realize that you can't actually do anything to win. It's pure random chance. This is why probably you don't play this as an adult. It's also why it's great for kids on long car rides, because hopefully they don't know yet that they can't actually win, and it can take a long, long, long time to make it your way through an entire game. We're going to use a simple variant for the purposes of this talk. On each turn, each player will play one card. If that card's value is higher than the others, that player wins and takes both cards. If the cards are equal, then a war begins, and each player continues to play cards until one of the pairs has a winner, at which point the winner takes all of those cards in that turn, and we continue playing. First code slide. This is actually in Ruby, and I wanted to show you what a procedural approach might look like. So here on line 1, we're going to gather our 13 times 4 cards into an array and shuffle them. Then we're going to partition that array of cards into 2 arrays, one for each player. And then while there's no winner, we gather the last card off of each hand, and then we'll talk about lines 5 through 7 in a second because they handle the war case. Lines 9 and 10, we determine the winner. Pretty simple check to see who has the higher card. And on line 10, we append the currently played cards to the end of their hand. Lines 5 through 7, basically, if they're equal, we just keep appending the cards to the set of played cards and keep checking for a winner until we can find one. But that's boring. Plus, we're at a Postgres conference, so why would we want to use that solution when we could instead use sets? So how would we define what we're going to do before we write a query? Here's my first attempt. A game of war can be represented as an ordered set of tuples, each tuple being dependent on the previous, containing the winner of that play and each player's resulting hand of cards. But there are a few issues with that definition. A set implies uniqueness of tuples, but we have to handle the possibility of repeats. This would imply a stalemate, and we need to end the simulation because there's no reason to keep going. More importantly, we need to know how we get our initial seed data, and we also need a base case to terminate. So I've revised it this way. An ordered set of tuples containing the winner of that play and each player's resulting hand of cards, where the first tuple has a null winner, and each player's randomly dealt hand of cards, and each subsequent tuple is the result of applying the game's rules to transform the previous tuple until either of the hands are equal. That would be a stalemate. Or one of the player's hands is empty, which means the other player won. Now, observation. We've defined the game of war here as a recursive function. We have all 3 components that you would need: an initial value, the recursive form, and the base case. And that sounds like a candidate for implementing this with recursive common table expressions. One more warning before we look at the actual SQL here. Since we're looking at some of my ideas that didn't work first, It's entirely possible that if you look closely enough, you'll find an error, whether that error is fatal or resolvable within a given approach. I'm planning to cover those issues along the way in the talk, but if you notice one I didn't catch, feel free to ask about that at the end. And now we'll start with some SQL. So we're going to be using this chunk of SQL for all three variants that we'll look at. And this is basically just setting up our deck and whatnot. So we have a CTE to generate all of the deck cards and randomize them. As a side note, if you're not familiar with generate series, I highly recommend looking at the docs for it. It's a fantastic function for filling in fake data or doing more interesting things, but it's particularly useful in that case, I think. And then we're going to assign a player index, 0 or 1, to every row or every card. We could do this more simply than using a window function, but it's another interesting demonstration along the way to use row number over here. And then finally, we'll actually aggregate those based on the player, and so that we have one tuple for each, or one row for each player. The results of that we'll walk through and look like this. So we have cards now. In all of these examples, I've trimmed the size of the deck down to be 4 cards in 2 suits in size so that we only have to display 8 cards because I don't want to display all over 50 cards on the screen at once. You wouldn't be able to read it. In the second part, again, now we've just assigned 1 and 0 alternating to each card. And then finally, we actually aggregate those so that we have an array of cards for each player. So the first version. In this one, I thought, well, each tuple could be the hand, just incrementing along the way, the player index, 0 or 1, and then the packet or the array of cards that they have. This means that we would have 2 rows per turn in the game, actually 1 per player. So let's step through that first part. This is the non-recursive side of the recursive common table expressions. How many people have used recursive CTEs at all? So a fair number of you. So you know that, to review, we have the non-recursive side, and then typically a union or a union all, and then the recursive side of the query that's self-referencing. So in this first part, we're basically just selecting the data from that shared values, because we're just going to start off the game at hand 1 with exactly what the player has. Next, we kick off the recursive side by calculating the last hand's results, which in this case, the first time through, is the seed data in the same form. Then the recursive side. We calculate the set of cards that each player will retain, which cards they're playing, and what their opposition is. So the retained cards is essentially here, that's on line 45 if you can see it. The retained cards is essentially all but the last card. Then we calculate their last card, and the max opposing card is just the inverse of the last card, the other player's last card, so that we can compare the two easily and determine who the winner is. And the result of this looks like this. We have the player index, and we have the set of 3 cards that they still have in their hand. We have the last card that they played, the cards that are now in play as an array, and we have the opposition card, which is just the inverse of the last card column. Moving down this long query that I couldn't fit on one slide. We have to shuffle the played cards so that when we prepend them to the winner's hand, we don't have any permanent cycles. This is something I actually did encounter, and my MacBook was at risk of overheating because Postgres was running for a very long time until I realized what had happened. We calculate the winner based on the opposing cards like we already talked. That's this case statement right at the end. And when we run that through by itself, we end up with data that looks like this. The first player won because the card that they played 3 was greater than 2, and they're the winner. So at the end, we increment the hand and prepend the played cards to the winner's packet. And then we continue in this where clause until we have a winner. That is, one of the player's packets is empty, or the player's packets are the same, which would be a stalemate. Now, this is the result that we expected from running our query. We now have the first player has a larger packet because they won those cards 3 and 2, and so they're at the beginning. And the second player now only has 3 cards. But when we actually attempt to execute the whole query, instead we get this. Error, recursive reference to query simulation hands must not appear within a subquery. I apologize, the line number in the error message doesn't actually match up to the demo SQL here, as I added in some comments above it. But if you look at lines 36 and 37 and also line 79, we reference simulation hands, which is the recursive common table expression, to find the max hand and to be able to find the actual result sets from the last iteration through. So an explanation. I think this is actually one of the bigger limitations on recursive common table expressions in Postgres. Inside the recursive component of your query, you can only reference the result set so far, the recursive data that you've worked on so far, once. You also can't refer to it within certain kinds of subqueries. You can't reference the recursive term in an exclude. So if you have a nested common table expression, you can use union, but you can't use exclude. You can, however, start with a reference in a nested common table expression and build further upon it, which we'll actually do in a later one to fix this problem. It turns out both of these problems can be solved relatively easily. But in my effort to keep the solution generic, that is, I wanted to see, like, could I write this up so you could handle an n arbitrary number of players? I missed that fact until I was working on this talk and after I'd already rewritten it twice. So don't over-engineer. Everybody has done this in the room, I'm sure. So let's look at the second version. We start by defining our seed data again. And in this one, I thought, well, 2 rows is a little bit hard to work with because it's a lot easier if you can just find 1 row and work on the same data at a time. So let's have our tuple be defined as a hand and then an array of packets. This could still actually handle, theoretically, an arbitrary number of players because we have an array in line now that can be of any length. So we take our shared data, which looks like this again, with 1 array for each, and we go ahead and merge it into an inline array that has both of the players' packets in line. This version relies on several joins. So the first part here might be a little confusing, the way we've had to break it up, because you see things referenced like pending cards, retained packets, and the winner value, and they aren't in this from expression, but we'll look at the joins as soon as we look at the from here. So in our first from clause, we're going to find the most recently played hand results, which in this case is just the seed data again. And notice also, instead of having select star from simulation hands where the hand equals select max from simulation hands, we've converted this into an order by and limit combination to avoid the nested subquery exclusion problem. Thankfully, that can be done in this case. I'm sure that there are cases in which it can't, which is why I say it's a real limitation of the implementation. And then in our first join, we calculate what cards each player will retain and the set of cards that they'll actually be playing as a whole. So some nastiness again here, but on lines 52 and 53, we're basically just using array length to get the second last position, basically, and chop the array into the first n-1 cards, and then take the nth card from each one and put it in its own array. A slight detour. What's that keyword lateral mean? Keyword lateral is a new join type that was added in Postgres 9.3. That's about 2 years ago. Sadly, many of us are still stuck on earlier versions of Postgres, and so The previous talk in this room, PG Logical, hopefully will help you get upgraded at some point, but this is a nice thing to read. The docs say this: subqueries appearing in the from can be preceded by the keyword lateral. This allows them to reference columns provided by preceding from items. Without the keyword lateral, each subquery is evaluated independently and so cannot cross-reference any other from item. Among other things, this allows set returning functions to be used more easily. We can laterally join to a set returning function that depends on previous from data instead of the much more odd and hard to read expand the set returning function inside of the select that I've seen and used before. This is much easier to understand. So here's how that first join works. We end up with the 3 cards in each retained piece and the last cards, and then we'll move on to the second join, and we randomize the pending cards again to avoid cycles. We also have to determine which player won. And as a side note, the logic here isn't quite right with respect to pending cards. We'd actually need to handle the war case and carry over any pending cards to the next hand, which isn't shown here. But we'll soon see that that isn't our largest problem, so I'll gloss over that. Here's what we would expect the second join to return, just that list of pending cards and that player 1 won. And of course, we need to keep executing our recursive component until we have either a winner or a stalemate. We finished the from component, so now back up to the select that we talked about earlier, and we expect that to generate this after that hand is completed. The hand has been incremented by 1. We've now played a turn, and the packets have 5 and 3 elements respectively. But when we try to execute this, I get this error. Function array length that takes the parameters integer and integer does not exist. And it provides a hint that we hope is helpful. No function matches the given name and argument types. Maybe you need to add explicit typecasts. This error is confusing at best. Looking at our code, it doesn't look like we've done anything that the error says we've done. We have nested arrays and we access them, and we never try to call the array length function with an integer and an integer. I'm trying to call it with an integer array and an integer. The error message, or the hint, suggests that we should consider adding typecasts to clarify to Postgres what we're trying to do. But that yields an equally mystifying error that says you cannot cast the type integer into integer array, which is self-evident but unhelpful. Those of you who are more familiar with Postgres' array implementation may have already noticed a critical flaw here. Multi-dimensional arrays are a lie. Well, really, they're matrices. But if you're expecting what other languages have, you'll be unpleasantly surprised. Essentially, each of the nested arrays, each subarray in a nested array needs to have the same size as the other subarrays. Multi-dimensional array access via the subscript operator is also not intuitive. Suppose that I have this valid multi-dimensional array of a nested integer array, and I access it at subscript 1, which, as a side note, is also consistently annoying for someone like me who works more on the procedural side more often. I expect this to be at index 0, not 1, but we'll just have to agree to disagree. Accessing it at index 1 returns a null value of type int4. Now, that is not what I expect, because clearly at index 1 we have an array, not an integer. Even more mystifying, if you access it at index 1 and then index 1 again, you actually do get a valid int4 value, as if you've accessed the array in the nested way that you expect. I don't have an explanation for this other than to say that it's hard to use multi-dimensional arrays, and if I remember correctly, there is much mailing list discussion about this limitation, in fact, and I don't think anybody has a solution. This version also suffered from one of the same problems as the first. We used the recursive component in a subquery, but like I mentioned earlier, we were able to replace that with an order limit combination and solve that error. So let's look at the final version. Hopefully this one works. So first we generate the seed data. Now, this one is a good bit more complex here because we also need to keep track of the pending cards across multiple turns when a war happens. And we're also going to track the number of wars. That's the 0 at line 33. Line 32 is the pending cards. And of course, we have a null winner to start off our game. A quick review again of the shared component of the code. We have 2 packets, 1 row for each player. And so now we generate our seed data, and it looks like this. We have all in 1 row, so again, we don't need to mess around with the multiple rows per hand. We have our 4 cards each for each player. The pending card starts off as empty, and there's 0 wars and no winner. Like the last attempt, this also depends on lateral joins. So we'll be looking next at where the retained packet, pending cards, and winner values come from. This was also the version that was hardest to fit on the screen because there are lots of long case statements here that there's just no good way to display enough of the code on the screen at once in a way that you can read. I apologize for that, but we'll walk through it quickly here. Basically, we're going to, on lines 41 and 42, and then the next 2 are essentially the same, or I guess there's 3 lines there. We check to see if we have a winner, and if we do, we have the pending cards and their retained packet merged together is their new packet. Same thing with for player 2. If there wasn't a winner, then we need to carry on the pending cards to the next round. Otherwise, if we're ending a war, we're going to make sure that that's empty. And then we also increment the war if we did have a winner last round, but we don't have one now. So the from piece is identical to the last one, I believe, other than the fact that the result set is now our new seed data for this version. We have to find the most recently played hand results, and that's just the seed data again at the first time through. In our first join, we've split the player's hand into the part that they retain and the card they're going to play. You see a running theme here, but a different implementation. And when we execute that by itself, we get this. We have 3 retained cards for each player, and the last card is 3 and 2. You'll see here that I've just given up on having more than 2 players. I am convinced that it can be done, but I finally decided that having a working solution was more valuable than being able to handle arbitrary cases that no one actually does. In our second join, we calculate what all of the in-play cards are, and they're randomized to avoid endless cycles. And then we calculate the winner. That winner calculation is trivial. Again, this line 82 might look a little bit odd at first, where c.n is greater than -1. Basically, in the previous, I'm not sure how far back I need to go for it, but we used the -1 as a filler card when the player doesn't have any more cards, because the -1 will always be the lowest card, and it allows us to easily maintain our numeric comparison without having to worry about nulls. And when we execute that piece, we get the pending cards as we expect, and the winner is the same again, since we're using the same data. And we continue executing that query in a loop until we found either a winner, or in which case one of the players has no cards left, or the stalemate where they're the same. So we finished the from components. Now we go back up to the top of the query and select. We increment the hand counter, because now we've played another turn. And we calculate each player's packet based on whether or not they are the winner, and increment the war count, and so on. So now, if the internet will work for us, this is a risk to do in the middle of a presentation, and if I can find my mouse. Let's try and So, and just to prove that this isn't cached, let's run it one more time. And we get this. And I'm always curious to see how many hands had to be played. In this case, 481. I've seen a couple thousand, and I've seen as low as maybe 100. This is why you have your kids play this game endlessly in the car on a long road trip. If your kids are smart, at some point they'll figure out this game is entirely pointless, and they'll stop playing it. It's more fun, I think, to write the SQL code than it is to play the game, actually. But that's is what it is. Performance implications. Now, I ran this query through the explain in the planner, and I know you can't read this, but suffice it to say it's a mess. There are cases in here where there are obviously arbitrary numbers, like the rows that are expected from this sort loop is 10 million, I think it is, and other places where it's an arbitrary like 35,000, and so on. But that's easily explained by the fact that we can't really tell anything valuable from this example because it's not operating on real tables. The planner doesn't have access to any statistics, and so it just throws up its hands and says, here's bogus data. We'll do what we want. But in reality, if we actually had data here, performance would scale inversely with the number of recursions that we're going to do. Every time through the loop, or every time you recurse, you're generating another query execution. So if you have deep recursion and an expensive query, the cost is going to rise rapidly, and your database server will not feel happy. Some takeaways. I find it helpful to restate complex problems in terms of a set definition when I'm trying to figure out how do I wrangle this problem into a complex query. It doesn't have to be a strict mathematical definition, but some kind of set understanding that also can flesh out some places where you haven't addressed corner cases. Common table expressions are far more powerful than they may initially appear. They aren't just for abstraction. They also allow us to do things that most people would assume are only possible in general purpose procedural programming languages. But actually, you can do it here. I've essentially just used Postgres in this talk as a remote execution engine. Some may consider that an abuse of Postgres. I consider it fun. But the SQL version here was harder to write and longer than the procedural version. But it was also more likely to work correctly, in my opinion, the first time through, at least once I was within what Postgres supports and didn't have syntax errors. That's because I don't have to write the code that actually executes this. I just have to describe what I want. This is an argument for declarative programming, right? But debugging infinite result sets is difficult. I have not found any good way to actually walk through what the executor is doing easily. Logging is also painful because you don't really have hooks to know, like, okay, how many times has this, like, is there an infinite loop? I can't walk through it. I don't know. I'm just guessing based on the fact that my CPU fan is running. So that's the end. Hopefully today's talk was informative, but also a bit more of a lighthearted way to learn about using recursive common table expressions. My goal here was that we have something you didn't have to understand a huge data model to work through, but still see them in practice. I have the talk online here on GitHub. There are also some further examples of more abstract or distilled down examples of nested CTEs showing that work, showing where the problems are, showing the array stuff we talked about and other things, as well as this presentation is also available there in Keynote form. So any questions? Yes? I will confirm that it is marked as public. I thought it was, but I will confirm that. Yes?
I know that CTEs are an optimization defense, but I think my question is a little bit difficult, and if they're a little different, then it's probably difficult too. One of the things I like using CTEs for is taking human equal P maybe and doing some little transformation on it and getting a result set
I do not, other than to say that this is pain that I have seen also. Like I said earlier, the fact that CTEs are an optimization fence is both a blessing and a curse. Sometimes we've used CTEs a fair number of times at Braintree to trick the planner into doing the right thing, because now it doesn't. We've disallowed it from inlining the code, and now it will actually use the right index. That's terrifying, kind of. And also not necessarily forwards compatible. There is a hard problem with how do you, Postgres doesn't have a way, unlike some other database engines, to hint to the query planner of what you expect or what you want to do. And there is an argument to be made that that is the correct thing to not allow that, because then you don't have to worry about you don't have to worry about the data changing. Like if you always trust just the statistics, then hopefully they're correct and your hint is not ever out of date. But also when you get into large data sets or cases like that, we work with terabytes of data, and so there is real pain here. The query planner does not always do the right thing, and sometimes it seems very unintelligent. Please don't take that as a negative on Postgres. I love working with Postgres, but there are times where it has surprising behavior. So I hope someone else has a better answer, but I don't.
The other way that you can do that is the offset zero trick, which does have an advantage of CTEs are always materialized in a table store. And if you're dealing with a large enough record set, that can become extremely painful.
Yes.
Then it's pulling all that to disk just to read it back in a single time.
Using offset zero basically to force it to.
Offset zero it's the exact same optimization fence that the CTE is, but it does not force, well, technically it does force a materialized node to show up in the plan, but the materialized node is smart enough to detect, well, actually it's something further upstream, but it can detect that, we don't need to do random access into this material.
We're just looping through it, and so we can keep using the index and so on.
Right, so it does, I think it actually, no, it actually doesn't even create the tuples. Whereas a CTE scan node always creates the tuple store. It always materializes into the tuple store. So, and I believe it's also set up so that it can't actually, sometimes in a tuple store you can remove data as you read it and you know that you're done. I don't believe the CTE scan can do that either. So one way that you can get that optimization fence is to just do a sub-select in your from clause and just stick offset zero in there, because offset and limit will force that fence to happen.
So the suggestion there is that sometimes if you inline what would have been in the CTE, if you add offset zero, you will trigger some of the optimization fencing behavior, because it treats it kind of like a materialized node, but doesn't necessarily execute it as such, like it would with the CTE, where we're going to materialize all of the rows, potentially to disk, to be able to use them later on in the query, which, like you said, is painful when you have large result sets in the CTE. Anything else? All right, thanks for coming today.